In the previous video, we have discussed about the complex number since the beginning, the basic concept for the complex number, until the polar coordinates in the Argand diagram. How do you convert from the Argand diagram in Cartesian, x and y, into the polar coordinates? Now we will continue to discuss about the algebra using the polar form. So let's recall the polar coordinates in the form of r and theta. R is the modulus, and theta is the argument. So for example, we have z, the complex number, in the form of r1 and theta1. And the second complex number z2, it has the modulus r2 and argument theta2. So in the polar form, we can write the complex number as r cos theta1 plus I sin theta1. And for z2 is r2 cos theta2 plus I sin theta2. If we multiply the z1 and z2, we will have r1 times r2 cos theta1 plus theta2 plus I sin theta1 theta2. So the modulus is being multiplied, and then the argument is the total argument. We know that theta is the argument, so argument of z1 plus argument of z2. We can prove this. So we multiply the z1 and z2. R1 cos theta1 plus I sin theta1 times with R2 cos theta2 plus I sin theta2. So I can just multiply R1 and R2, and then I will have cos theta1 plus I sin theta1 multiplied with cos theta2 plus I sin theta2. And this is equals to R1 times R2 cos theta1 cos theta2 plus I cos theta1 sin theta2 plus I sin theta1 cos theta2, and then plus I square sin theta1 sin theta2. And this is equals to R1 times R2. We can change this. I square is a negative 1. So we have cos theta1 cos theta2 minus sin theta1 sin theta2. Cos theta1 cos theta2 minus sin theta1 sin theta2. And then the imaginary parts will be sin theta1 cos theta2. I switch the position. Plus cos theta1 sin theta2. I equals to R1 R2 bracket. Nah, cos theta 1 cos theta 2 minus sin theta 1 sin theta 2, we can change it into cos theta 1 plus theta 2. If you remember, using the addition formula of trigonometry, cos A plus B is cos A cos B minus sin A sin B. So this is the identity. Plus, and for the imaginary part, we have sin theta 1 cos theta 2 plus cos theta 1 sin theta 2. And this is sin theta 1 plus theta 2 I. Yeah, using the formula sin A plus B is sin A cos B minus cos A sin B. So this is. So from here, we have proof that the multiplication of two complex numbers in polar form equals to the multiplication of the modulus times with the cos of the total argument z1 plus argument z2. So this is for multiplication. And using the same method, we can prove that if we divide two complex numbers z2 over of z1 over z2, so we just divide the modulus and then the argument will be argument z1 minus argument z2. And the argument for the cos and for the sine should be the same here. It cannot be different, it should be the same because that's the definition of the polar form. So in summary, if we want to find the modulus of z1 times z2, so that's the same as we find the modulus of individual complex number, and then we multiply it. And for the argument of the multiplication of two complex number is equals to the argument of C1 plus argument of C2. And also, if we divide the complex number Z1 and Z2, we want to find the modulus of Z1 over Z2. So that's the same thing as Z1 modulus of Z1 divided by modulus of Z2. And for the argument itself, it will be argument Z1 minus argument Z2. And then next is the exponential form. The complex polar form can be expressed also in the form of exponential using the definition e to the power of I theta is cos theta plus I sin theta. So that means before we have c equals to r cos theta plus I sin theta. Now I can change this into e I theta. So therefore we can express c equals to r times e to the power of I theta. You can open the Collins textbook and then see the examples and the exercise on the page 262 and 200 until 264. the Moivre theorem. This theorem is a bit important to solve the complex number algebra using the method founded by the French mathematician Abraham de Moivre. So let's see, we have the complex number z equals to r cos theta plus I sin theta. So if we have the z squared, it's z times z. So according to the rule before, if we multiply the z, so we multiply the modulus and then we sum the argument. So that means this is r cos theta plus I sin theta times r cos theta plus I sin theta. So that means we can have r squared and then cos theta plus I sin theta plus theta. Yeah, you see the identity here. So that's why we can write as r squared cos theta plus theta become cos 2 theta, and I sin theta plus theta become I sin 2 theta. So from this example, we can see that if we have z squared, so this is equals to the r squared, cos 2 theta plus I sin 2 theta. Therefore, for any rational number of n, so z to the power of n will be r to the power of n, cos n theta plus I sin n theta. So this is the Moivre theorem. Here are some exercises you may try this for your own practice. And then I will continue with the loci in complex plane. We have several types of shape of the loci in the complex plane. The first one is the circle. So for example, suppose we have C in this form, Z in this form, Z minus 1 absolute equals to 2. So we know that absolute sign is the modulus. So the modulus of Z minus 1, or I can rewrite this as Z minus 1 plus 0 I. Equals to 2. Now the modulus itself is the distance from Z to the coordinate of 1 plus 0 I. So if we draw in the Argand diagram, this will be the distance between Z and the coordinate of 1, 0. So 1, 0 is this 1, 0. So we can find the set of solutions of the complex number Z that has the distance of 2 from the coordinate of 1, 0. So if we use the distance formula, we know that Z is x plus iy. So to find the formula between the z and the coordinate here, we can use the Pythagoras. So it's Pythagoras, or I can rewrite x minus 1 square plus y minus 0 square. Yeah, we can rewrite this as x plus iy minus 1. So I can collect, yeah, I can collect x minus 1 plus iy. So in this case, the modulus of this will be x minus 1 square and y minus 0 square. And this is equals to this one, 2. So if I square both sides, I will have x minus 1 square plus y square equals to 4. If you notice, this equation is a circle equation with center of 1, 0, and the radius is, this is r square equals to 4. So radius is 2. So that means the locus of z minus 1 equals to 2 is a circle with center 1, 0 and r equals to 2, radius 2. So we draw it, the center 1, 0 with the radius of 2. So this is 3, 0, and then we draw a circle like this. So from this example, we can see that this locus will be a circle. This one, for example, yeah, we can see the exercise number 1a. Illustrate the locus of z in the complex plane if z satisfies modulus z minus 3 plus 2i equals to 5. So from here, we can say that this will be the center of the circle. So the center will be 3, 2, and the radius will be equals to 5. You can see from here, the center 1, 0 is taken from here. 1 plus 0i, the center, and the radius is this one. So the same, this is the center, and the radius will be 5. So you can draw it. So 1, 2, 3, 1, 2. So this is, and the radius will be 5, like this. That's for A. C. This is A, and for C, Z plus 2i equals to 2. So I can rewrite as Z minus negative 2i equals to 2. Or I can rewrite again, Z minus 0 minus 2i equals to 2. So the center will be 0, negative 2, and the radius will be 2. So we can draw. This is the real, yeah, and this is the imaginary parts. And the center 0, negative 2, so negative 2 here, and the radius is 2. So it starts 0, 0, yeah. The radius is 2. Yeah. So this is the locus of the circle. The second type is perpendicular bisector. The perpendicular bisector has notation the same. Z minus A, yeah, is a distance from a complex Z to a certain point complex coordinate A in the Argand diagram in the complex plane. So that means if we have Z minus A modulus equal to Z minus B modulus, so this has a meaning of distance between the complex number Z to the complex coordinate A that has the equal distance to the complex number B. Yeah? So before, if we have Z minus A equals a number, so this is the distance from Z to the point A has the distance of K. So that's why it is a circle, because this is coordinate A, and then the Z should be in equidistance of K. This is Z. Will be equidistant from coordinate A. So it is a circle because the Z should satisfy all the points on the circle. So it will be equidistant to all the directions. Now, the distance of Z to A equal to distance of Z to B. So that means the only possible region that equal distance to both of A and B is the perpendicular bisector. So in this case, we will draw it. This is coordinate A, for example, and this is coordinate B, for example. I can have the line connecting A to B, and the point that has equal distance from A and B should be in the perpendicular bisector, like this. So the distance from Z here, somewhere on the line here, will be equal distance from both A and B. Or another Z here, it will be equal distance. Or maybe Z here will be equal distance from both A and B. So this is a perpendicular bisector. Yeah, we know that Z, the complex number, will satisfy the line, the blue line here, the perpendicular bisector line. So the Z will lie on the blue line, on the perpendicular bisector. So let's see the example. Describe the path of point which moves fixed plane so that it always same distance from two fixed point A and B. So in this case, Z plus 3, I can rewrite as Z minus 3 plus 0i. Z minus 4i is Z minus 0 plus 4i. So that means this is the coordinate 3 and 0. This is the coordinate 0 and 4. So I can just draw 3 and 0, 1, 2, 3 here, and 0, 4, 1, 2, 3, 4 here. So this is the coordinate, yeah. This is the Z1 and Z2, Z1 and Z2. And the distance, the set of solutions of the complex number that has the same distance from both Z1 and Z2 will be in the perpendicular like this, perpendicular bisector. It should be perpendicular, yeah, bisector. So maybe in the calculation, we need to calculate the gradient of the line so we can draw it accurately using the equations of the line, yeah, using algebra. But for the sketch, we can just sketch it. Yeah, we can just sketch it inaccurate, just showing the trend that the line will be the perpendicular bisector. Yeah, bisector means it will pass through the midpoint. For example, number 3 again. So z equals to this. So that means this is the distance of z minus 0 and z minus -2 plus 2i. So the coordinate will be 0, 0 and -2, 2. So it will be 0, 0, -2, 2, 1, 2, 1, 2. So this. And it will be the perpendicular bisector. So this is the solution of the complex number that has equal distance to both 0, 0 and -2, 2. And by writing the z x equals to x plus iy, we can find the same results algebraically. So we know that the distance is z minus 0 equals to z minus -2 plus 2i. So this is x plus iy minus 0 equals to x plus iy minus plus 2 minus 2i. Simplify. So this is x plus 2 plus y minus 2i. And then we know that this is the distance, the modulus, so square root of x squared plus y squared. And for this is the real part, so square root of x plus 2 squared plus y minus 2 squared. And then we square both sides. So we have x squared plus y squared equals to x plus 2 squared plus y minus 2 squared. So expand x squared plus 2x, 4x plus 4 plus y squared minus 4y plus 4. And we see here we can cancel x squared and x squared, y squared and y squared, and it is reduced to 0 equals to 4x minus 4y plus 8. Or I can just simplify x minus y plus 2 equals to 0. So this is the equation of the line of the perpendicular bisector. This equation. So using the algebra, we can find the equation of the line where the complex coordinates c lie. If you want to use the coordinate geometry, it will be fine also. So this is 0, 0. This is -2, 2. So we know that I give this name A and B. So the gradient of AB is 0 minus 2 over 0 minus negative 2. So the gradient will be is negative 1. So that means the gradient of the perpendicular bisector will be equals to 1. And since it is a perpendicular bisector, so it will pass the midpoint of AB. So find the midpoint, negative 2 plus 0 over 2 and 2 plus 0 over 2. So negative 1 and 1. And then we can find the equation of the line, y equals to mx plus c. So the gradient is 1, so 1x plus c. So replace the midpoint because the perpendicular bisector passed through the midpoint, so we can replace the midpoint. So 1 equals to 1 negative 1 plus c. So 1 equals to minus 1 plus c. So c equals to 2. So that means the equation will be y equals to x plus 2. Or we can rewrite as x minus y plus 2 equals to 0. Yeah, the same result. Next, half line. The notation for half line is argument of z minus z1 equals to theta. Is the half line starting at z1, which makes an angle of theta with the positive real axis. So these are the keywords when you have the argument. So it should be a half line starting for this coordinate. Make an angle of theta with the real axis. So this is the coordinate, half line. So starting from this and then move away and make an angle of theta from the real axis. The direction of the line will follow theta. Yeah, so if the theta is negative, for example, the theta is negative minus theta, so you will move here. So let's see the example. Draw the locus of argument z minus 3 plus 4i equals to pi over 3. So from here we know that the coordinate of the complex number is 3 and 4. And the theta will be positive pi over 3. So we can draw 1, 2, 3, 4, 1, 2, 3, 4. So 3, 4 will be here. And then pi over 3 positive from the real axis. So if this is the real axis, we draw pi over 3, so around here. So this is pi over 3. So this is the half line. How do you draw the half line? Yeah? Next, draw a locus of argument z minus 4 minus 2i equals to negative pi over 4. So that means the coordinate will be 4, negative 2, and the theta will be negative pi over 4. So you draw 1, 2, 3, 4, 1, 2. So this is the coordinate. And then negative pi over 4, this is the real axis. Negative pi over 4 is here. So this will be the z. Yeah, so the z, the complex number, will be lie on this line, on the half line. So in summary, we have several notations. If we only have z1 minus z2, that means we are looking for the distance between the two complex coordinates. If we have z minus z1 equals to r, so that is a circle centered at z1 and the radius r. If we have z modulus z minus z1 equals to modulus z minus z2, so that means it is a perpendicular bisector of the line segment joining z1 and z2. So perpendicular bisector. And if you have argument z minus z1 equals to theta, so this is a half line starting at the coordinate of z1, makes an angle of theta to the real axis. Now we move on to the inequalities. To solve the inequalities problem, we need to draw the loci of the complex number from the previous subchapter. From here, yeah, from the previous subchapter. So we draw it first, and then after that, we can determine the region that will satisfy the complex inequalities. So for example, number one, illustrate on the Argand diagram the locus of the point which satisfies this. So here is z minus 2 plus 3i greater than or equals to 5. So first we have to draw that this is equals to 5. So what is this? This is a circle. Yeah, this is a circle with center 2, 3 and radius 5. So we draw. The center is 1, 2, 1, 2, 3. So this is the center and the radius is 5. So it will be like this. This is the equation equals to 5. But now we have to find greater than 5. So that means the solution of the z is not on the line, yeah, not on the circle, on the line of the circle, but it will be on the line and outside the circle. So the set of the regions of the complex number that satisfy this inequality will be the z outside of the circle, center at 2, 3, radius 5. Yeah. If the inequalities is z minus 2 minus 3i greater than 5, yeah, not there is no equal sign there. So you have to draw it in this line. 1, 2, 1, 2, 3. So you have to draw it in this line because it's not included. The radius is 5, and you see the region outside the circle. If this is without the equal sign. Next, find the locus of points for which z plus 1 plus 2i equals to z minus 1 minus 6i. So this is the point of z minus negative 1 plus 2i and z minus 1 plus 6i. So the coordinate will be negative 1 and 2, 1 and 6. So if we draw negative 1 and 2, so here I name it A and this is B, 1 and 6. 1, 3, 4, 5, 6. This is A, this is B, 1, 6. A is negative 1, 2. So I can connect the line. And this type is the perpendicular bisector. So I can just draw it perpendicular to the line. Now we can find it using the algebra. So we can find the midpoint of AB first. The midpoint of AB is negative 1 plus 1 over 2, and then 2 plus 6 over 2. So equals to 0 and 4. So the midpoint will be 0, 4. So it's around here, yeah. And then the gradient of AB will be equals to 6 minus 2 over 1 minus negative 1. So equals to 4 over 2 equals to 2. Now we find the gradient of perpendicular to AB. So the gradient of perpendicular to AB is negative 1 over 2. So the equation is equals to negative half x plus c using the y equals to mx plus c. And then because it passes through the midpoint, so we can just replace the midpoint. 4 equals to negative half x plus 0 plus c. So c equals to 4. So that means the equation of the perpendicular will be y equals to minus half x plus 4. So this will be the equation of the locus of the point that satisfy this equation, this complex equation. This is A. How about B? B illustrate on the Erdős diagram that the point which satisfies this smaller than this. So I can draw it using the gradient. So find the region that the distance of Z to the point of 1, negative 1 and 2, we know this, yeah, is smaller. So that means this will be shorter to the coordinate of 1, 6. So that's the definition. That's how you read this inequalities. So find the region where the complex number is shorter to this rather than to 1.6, 1,6. So which region is shorter to negative 1, 2? So negative 1, 2 is here, A. So the Z will be shorter to the coordinate A rather than to coordinate B. So that means we have to choose the two regions of, from the line that one of them should be shorter distance to A rather than to B. So in this case, I will select this area because all the regions here will has the shorter distance to A rather than to B. For example, I have this coordinate z. So the distance from z to A will be shorter than the distance z to B. And this is the inequalities, shorter, smaller than. So this is how you see it. One side of the perpendicular bisector's region. That's number 2. And the last number, illustrate on a diagram the locus point which satisfy of the argument. So that means this is the argument starting from z minus 2 plus 0i. So the coordinate will be 2, 0. So we draw 1, 2. So this is the coordinate. Start from this. And then we have to draw it to half lines. So it is 2/3 and pi over 4. 2/3 pi and pi over 4. So what is pi over 4? Pi over 4 is this. So this is pi over 4 from the real axis. And then for the 2/3 pi, it will be like this. This will be 2 pi over 3. So the argument that lies between pi over 4 and 2 pi over 3 is in this region. So we set that region. So these are the discussions about the complex number, especially using the polar coordinates and how do you express or illustrate it in the Argand diagram for the equation and inequalities. So that's all for this topic. Thank you for watching and bye.